molecular shape and polarity lesson. So today what we're going to be doing is we're going to continue our study of covalent compounds or molecular compounds, and we are going to start looking at them three-dimensionally. So there is a theory called VSEPR, so VSEPR, so valence shell electron pair repulsion. So basically, with this theory, we're going to use it to help us determine what kind of shape or arrangement, I guess, it's going to have. So we can call it the geometry of the molecule. So when you see a formula for a compound, you can't use it to kind of predict the shape. So what you need to do is you need to analyze, drawing some Lewis dot structures and analyze kind of what's happening with the electrons that are being bonded and the electrons that are they're not involved in the bonding, so they're just the lone pairs. So looking at these different aspects of the molecule, we're going to figure out the geometry, kind of the arrangement that the molecule has to form. And in order, like it all comes down to, we don't want the electrons, if there's some lone pairs here and some bonding electrons here, we don't want them to get too close to each other, right? They're going to have that electron-electron repulsion. So remember, when like charges come close, they will repel. So they're trying to minimize that repulsion, and so therefore the molecule will form a certain shape, a certain geometry. So once we use VSEPR to, figure out the geometry of the molecule, we're going to, actually name it, this is the shape, this is the shape, and so forth. And then from there, we're going to bring back electronegativity into our studies here and determine, because again, we've already studied electronegativity. We figured out within a bond what's going on with the electrons, right? So today what we're going to look at the what's happening in the overall molecule today. Okay, so we're bringing electronegativity back in order to figure out if a whole molecule is polar or nonpolar, okay? Not just the bond. All right, so that's kind of the gist of the whole lesson, right? So we're going to figure out what kind of shape that the molecule is going to form into. Then from there, we're going to figure out whether it's going to have poles, right? But if it's going to be polar or not, because that can lead us into our next lesson after this called intermolecular forces. But anyway, we'll get to that later. Let's start off with our VSEPR theory here. Okay, so we're going to go through step by step looking at different properties in order to build towards our shape. Okay. All right, so here's the first thing that we have to analyze, the axe notation. Okay, so in general, you're going to have we're going to analyze the central atom. So we studied this before. The central atom is always the atom that's in the compound that has the highest bonding capacity. So, so when we draw a Lewis structure, so for example, like we drew carbon, right? So it has 4 bonding sites, right? So it's got a high bonding capacity. So versus if you have like, so this is a high bonding capacity. So, if you, for example, versus like chlorine. Chlorine has a low bonding capacity because it only has the one spot, okay, where an atom can come in and bond, right? So where carbon has 4 spots where it can bond, okay? So I'm just going to get that out of there so it's messy. Okay, so the central atom will always be the one that has the highest bonding capacity of all the different elements that are involved in the compound. And so that's going to be A, and then X will be any of the peripheral atoms. So peripheral, in the sense that these other atoms that come along and attach to the central atom. So like, for example, hydrogen could come along. It's considered peripheral. It would come along and attach to the central atom carbon. And then from there, the letter M stands for how many of these peripheral atoms are involved. Okay, so again, we're looking at a compound. We're going to analyze what's the central atom, how many things are attached to the central atom. Okay, so X will be the like hydrogen there. And then we'll have E is the number of non-bonding electron pairs. So basically, these are the lone pairs that we were studying as well. They were just there hanging out. So like we got a lot of lone pairs here, right? These are all the lone pairs on chlorine here, but then here, this is the bonding site for chlorine. So we're looking at, so if chlorine was the central atom, that's what we're looking for. But if we're looking at carbon, we're looking for any lone pairs, non-bonding electrons that are involved, and that's what the E will be here, okay? So I added my little, some notes here to show you that, yeah, here, these pairs here are the lone pairs on chlorine, okay? So they're the non-bonding electrons. Carbon has high bonding capacity, has 4 sites that you can bond with, so it's a high bonding capacity, so it's a good example of what we consider a central atom. And then things would attach to it, like hydrogen has 1 spot, okay, it's a low one bonding capacity of 1, so it's a good example of what would be a peripheral atom, okay? Same with chlorine, good peripheral atom, okay? All right, anyway, so I'm just kind of throwing some pieces at you here, but let's actually look at it as a whole piece, like a whole compound here. So let's look at water, okay? We've studied water already. So we would have found that water, okay, so when you're looking at it here, when you build your, your Lewis structure, so we built our Lewis structure the other day with water, we would have found that there, the oxygen is the higher bonding capacity element here, so it goes in the middle, and then hydrogen attaches. So you change any bonding electrons to dashes, and then any electrons that are not being bonded, you leave as dots, okay? So again, this is the Lewis structure. So, so when we're looking at this piece here, we're going to start analyzing water in order to figure out, is it just a straight line, or actually does it actually have a shape to it, a certain shape to it, okay? So in a way, we're going from a 2D to a 3D model here. So, so we're going to start with the ax notation. So we'll use ax notation here on water. So again, A is the central atom, okay? So A is going to be the oxygen, right? Okay, like that. So we have oxygen there. So we just write A. And then we have peripheral atoms. That'll be the H, right? H will be the peripheral X. So hydrogen will be the peripheral atoms. Okay. All right, so how many peripheral atoms do we have? So we have like that are stuck to the oxygen, right? So we're not going to change A to oxygen or anything. We're just going to leave it as A. So having A here, that's the central atom. We have 2 hydrogens, so we're going to represent the peripheral atoms with an X. We have 2 of them, so I'm going to write the number 2 as a subscript, okay? So that's what the M value is here. All right, so then from there, we need to analyze the E. These are the non-bonding electrons, okay? So and again, where are we looking for these non-bonding electrons? On the central atom. The central atom is oxygen. So how many non-bonding electrons or lone pairs do we have on the oxygen? We have 2 of them, like that. So there's the ax notation. So you would write A with X of 2 and E with the 2, okay? Okay, so once we get the ax notation, we're going to look at the steric number, okay? And then from there, you should be able to predict the shape, the geometric shape of the compound, okay? All right, so with water, this is what we found. So now we go to steric number. Steric number, all you're doing here is adding the subscripts, the numbers that were on X and E, okay? So when we do that, so let's take a look here. So we take these 2 here. Okay, let's do there, and we add them together. Okay, so then you'll get, so for the water here, the steric number is, okay, 2 plus 2, which is 4. Okay, so once you find the steric number here, you're going to look at this table down here, and you can predict the shape. So they'll call it the electronic geometry. So the geometry, the shape, taking into account where these extra electron pairs are that aren't involved in bonding. Okay, so if you get a steric number 2, okay, you have a linear geometric shape. Okay, if you have one that's 3, then you'll have a trigonal planar, 4 tetrahedral. Okay. All right, so yeah, so just kind of look at those and just go, okay, so if it's like that, you just have if you could look at the actual compound, it would be a straight line. Here it's kind of like three things coming out of the central atom. Tetrahedral, I know this is a new shape for you guys, but this is how a chemist writes things three-dimensionally. So if you're right in the paper, right, you draw like a straight line like this. Okay, so these are, if this molecule was sitting on the paper, it would be completely flat in line with the paper. Now, if you have a diagram like the tetrahedral diagram, though, so you have A, and you have these two bonds, they're right in the paper, okay, so right flat with the paper. But then a chemist shows when one sticks out of the paper, they will draw a triangle like that. So this is coming out of the paper, and then if you're going behind the paper, you're drawing a dotted line or a dashed line, okay? Okay, so I just added some notes here. So basically, all right, the dotted line, just imagine it's going out behind the paper. So think of the paper, it's like it's the paper right on the table, or it's like a window, right? So these two lines are in the window. This one goes behind the window. This one comes out of the window. So I'm just calling it the plane, right? The plane, it's behind the plane, in front of the plane, or in the plane, like that, okay? So I know it's a little hard to see it three-dimensionally, but that's how a chemist draws it. All right, so yeah, so kind of this is the VSEPR theory here in order to determine the actual shape of the molecule. So again, we find the Ax notation, then the steric number. Okay, all right, and then we use this table here in order to determine the shape. So generally for Math 11, what we're going to do here is we're going to stick with steric number 2, 3, 4. Okay. But I just want to let you know that here's a little bit more detailed diagram here. So we have A with the peripheral atoms, right? It's forming a linear shape. This one's trigonoplanar, tetrahedral. We're going to have some that are bent, some that are trigonal pyramid, and others that are bent here with two lone pairs like that, okay? But then know that there are actually, there's steric number 5 and 6 as well, so you can kind of analyze these other shapes, and this is if you continue your studies with chemistry, you'll kind of analyze these other ones as well, okay? So for now, here is the, so this is the table that you're going to use. You're going to use the Ax notation and the steric number in order to predict the shape, okay? So once we kind of get that going, we'll kind of move and figure out polarity and stuff like that. All right, so the first example we're going to try is we're going to analyze the diatomic molecule of chlorine, okay? So Cl2. So we're going to go through the process of drawing our Lewis diagram. So this is what we did before. So think of this as like the two-dimensional diagram. And then from there, we'll determine our Ax to figure out our steric number in order to predict our electronic geometry. So that's what we were doing here. We're trying to figure out which one of these it was, okay? And so we'll draw it kind of in a similar format here where we'll draw the central atom and the peripheral atoms, and we'll also draw the lone pairs on, okay? And look at the geometry. Then we'll look at molecular shape after that. Okay, I just realized I forgot to actually finish that example that I started with here with the water. Okay, so we found our Ax notation. We found our steric number was 4 because we added the two subscripts here. And then we're trying to figure out, okay, what kind of shape it is, okay? So these are the general, some examples, okay? These are some examples, okay, of possible shapes. Okay, but there's a more thorough table on the next page here, okay? All right, so if we go over here, we'll see that we have, so we have a steric number 4. Remember we found steric number 4 for water? Okay, so we're trying to figure out, it's one of these three shapes here. So if you have 4 items on the central atom. So if we're looking at water here, we found that we have 2 peripheral atoms and we have 2 lone pairs. Okay, so which one does that match here? So if we're looking at the steric number 4 here, see how this one has 4 peripheral atoms on it? Okay, so water would not be considered to be tetrahedral. All right, so let's look at the next one. So look at this one. So we have our central atom A, and then we have 3 peripheral atoms, and then we have a lone pair. Okay, water had 2 lone pairs and 2 peripheral atoms, so not this one either. So then we'll look at the next one. We have 2 peripheral atoms, and then we have 2 lone pairs. That's the one we have. Okay, so that's what water is. So, and then if you look at the steric number as well, see it matches in the diagram as well, right? All right, so you're going to now specify what shape water is. So you would say water is the bent shape. So yeah, just a simple description, bent shape, okay? So you could just say, therefore, water is, I don't know, has a bent geometry shape, I guess. Bent electronic geometry. Let's get really fancy here. Okay, so we're taking into account the electrons, okay, the peripheral atoms, and determining it has a bent shape like that. Okay. Okay, so I've created the Lewis diagram here. So again, I took the Lewis dot diagrams of the chlorine atom. You'll find that, remember, they come along and they end up sharing this electron here that they have. So that's why I make a dash here for the bond. And then I left the lone pairs by themselves like that. Okay, so this is the 2D Lewis diagram. So again, we're going to go through and figure out X. So in this case here, you're like, okay, we need a central atom. Which one's the one in the central? They're both the same. So all you have to do is just, pick one. Just say, like, maybe the one on the left was going to be the A, okay? So in that case there, A, if the one on the left is A, how many peripheral atoms do you have? That's the X, right? So you can think of this one as the X, right? Like that. So how many peripheral atoms do we have? So if the left is the central atom, there's only one peripheral atom, like that. Okay, and then on the central atom A, the one on the left, how many lone pairs are there? Like non-bonding electrons are there? Okay, so you'll find that there's 1, 2, and 3 of those. So 3 non-bonding electrons. Okay, so I don't know, maybe I'll circle them to remind you. You're looking at these notes later, okay? So those are the non-bonding electrons. There's 3 of those. This is the peripheral atom on the right, and there's only one peripheral atom attached to our central atom, which is the left chlorine. Okay, so we have our X notation there now. So from there, we're going to go to our steric number. So remember, we're going to add the subscripts for X and E. So 1 plus 3, our steric number is 4. So just like water, we had this result before. This means that so then we go to our table up here, and we're looking at, okay, it's going to be a tetrahedral type geometry. Okay, so once we figure out the steric number, we're going to go through here, and so basically, see how all of these, they have a certain shape to them. So that's what we're going to do here. We're going to draw their central atom, remember the one on the left, the chlorine on the left, and we're going to write this here. Okay, so now you can see, I know it's kind of like this was flat in the page, but I was just trying to show you here, kind of keeping the chlorine, like here's the central atom, here's the peripheral chlorine atom here, okay? All right, so, and then here are the 3 non-bonding electrons that are attached. See, these green ones here. So I don't know, maybe I'll keep matching up the colors here. So you have our green, our lone pairs here. 1, 2, 3, like that. Okay, so they're there. I know they're not sticking straight out like that, but like I want you to think it is, they're there. They need that space. These lone pairs, that lone pair needs that space. That lone pair is out behind the back of the page. That it needs that space. And then here's the chlorine also attached to the other chlorine. Okay. All right. I'm not adding the lone pairs on the peripheral atom. So from here, I'm trying to show you that it's coming out of the page. So here's more of here's a 3-dimensional picture I found. So you can take a look and see, like this is methane. So you have carbon, and then you have hydrogen, and this hydrogen, they're in the page. But then this hydrogen, okay, sticks out of the page, and that hydrogen there sticks behind. Okay, so we're going with that whole, it goes like this, goes like this one sticks out, this one goes behind. Okay, so I know like these diagrams, it's kind of hard to visualize that, but that's what's happening. Okay, so you have to kind of get used to that format. All right, so from here, so this is the electronic geometry. I want you to now get to the molecular shape. So if we're not paying attention to drawing the lone pairs, what does this shape look like? Okay, so if you look at just the chlorine here, so you'll find here, if we're just looking at the chlorine here, chlorine to chlorine, all it's doing here is creating a straight, a line here, right? It's just a straight bond like that. So if we want to draw that now without drawing all the other extra stuff, we'll see that chlorine to chlorine is just a linear molecule. Okay, so like I know here we had a tetrahedral geometry, okay, but here, this shape here, without looking at the other electrons here, it's still like even these other non-bonding electrons, sometimes they distort the shape, change it a certain way. But in this case here, chlorine to chlorine, it's just gonna be a straight line. So it's gonna be a linear shape like that. Okay. All right. And yes, that's kind of where we're trying to get to today, just with the getting to the shape. So now that we have the shape and we've labeled it linear, what I want you to do now is, now we're going to start looking at the bond between chlorine and chlorine here, okay? So we're looking at the electronegativity values. So if we put chlorine and chlorine here, we're looking at an electronegativity value. So you're just going to go to your periodic table here, right? And look for chlorine. So chlorine has a 3.0 electronegativity value. Okay, so we'll put that on here. So 3.0, 3.0. So like we studied the other day, this specific bond here, you're going to find that it's tied. The tug of war for the electrons in the bonding electrons here is tied. So you're not going to have one chlorine have kind of more of the electron cloud compared to the other one. Okay, so in this case here, because this bond here, because we're looking at just the bonds within the molecule, this is the only bond anyway, you would say that this is a non-polar covalent bond. Okay, so we're just kind of bringing back what we did the other day with labeling the types of bonds that were involved in the compounds, okay? All right, so the non-polar covalent bond. That's what we need to look at here. Okay, so we're going to take it to the next step now. So if we had a more complex molecule, we'll have lots of different branches coming off the central atom. So we would have to study the electronegativity within all of those. And again, we don't need to write any partial charges here, so no partial charges. So now what we're going to do is, now we're going to the next box, go to the next box here, and we're going to look at the overall molecular polarity. So since we didn't have to have any, so there's no partial charges here, right? Because it's tied, no partial charges. You're not going to have a slightly positive and negative end to the molecule, right? So there's not going to be any poles. So when we analyze the overall molecular polarity now, that's the last step of our study today, we need to ask ourselves, yeah, do we have poles? But we don't because it's like a symmetric molecule. You can think of it that way, right? It's chlorine and chlorine. So they're going to have a tie when it comes to the tugging on those electrons. So you would say in this case here, this overall molecule is a non-polar molecule. Okay? All right. So that's what we need to do today. We need to go from two-dimensional to three-dimensional diagram. Then from there, we need to figure out is the overall, like once we figure out what shape it has, we need to figure out whether it's going to be an overall polar or non-polar molecule. So is it going to have a positive and negative end to it? Okay, so chlorine gas, nope, that's not going to happen. It's just going to be a non-polar molecule. Okay, all right, so again, we will lead into a new lesson after this once we figure out the polarity of molecules, but for today, that's all we're doing. So we'll try another example here. We'll look at, again, so this is your nomenclature practice. What molecule is this? Okay, it's ammonia, right? So maybe even jot that down, ammonia. Okay, so it's I don't want you to write nitrogen trihydride. Okay, so memorize ammonia. Okay, so ammonia. So let's, again, same thing, go through the steps of creating a Lewis dot diagram. So ammonia has 5 electrons. Only 2 of them are bonding, or, oops, sorry, 5 electrons. Oops, that's my percent. So it has 5 electrons, so there's only 2 or 3 bonding sites, right? So one site already is taken up. The lone pair is already there. Okay, so then from there, what am I attaching to the nitrogen? I'm attaching hydrogen, so 3 of them. So 1, 2, 3, like that. Okay, so this is kind of practicing all our lessons here. So there's that sharing, and there's that sharing. That's going to happen. Okay, so again, we have a non-metal and a non-metal coming together. So here is the Lewis diagram. Okay, so our little 3-dimensional diagram here, and we're going to use VSEPR now in order. So valence shell, you should know what VSEPR stands for. Valence shell. So because again, we're looking at just the valence electrons. So the valence shell electron, and then we're looking at how there's that repulsion. Okay, so valence shell electron pair. Okay, when we have these electron pairs, they're going to obviously repel each other and distort the shape of the molecule. So yeah, so going through the steps of X and steric number, we are going to determine what the shape is. Okay, so A, remember that's the central atom. What's the central atom here? Nitrogen. Nitrogen is attaching to, or is being having the various hydrogens attached to it, so it's the central atom. So A is there. All right, so then from there, X. Okay, so X, here we'll change it to a different color here, X. Okay, so X, these are the peripheral atoms, right? So that's your X, right? And here I'll just say nitrogen's your A, okay? So X, there are 3 peripheral atoms, okay? 3 peripheral atoms. So you're going to write X subscript 3 like that, okay? And then E are those lone pairs, right? The electrons that are not involved in bonding. So you would say there's one of those, okay? And then someone always asks, because they do this in math, do I have to write the one? Or, we do this in our chemical formulas as well. If you wrote your X like this, that is okay. Okay, so then from there we need to find our steric number. Our steric number again is just adding the subscripts that are on the X and the E. Okay, so 3 plus 1, oops, 3 plus 1 is 4. Okay, so we got another one that's the tetrahedral family here. Okay, so tetrahedral, trigonal, pyramid, or bent. Okay, so we're looking for the electronic geometry here. Okay, so okay, in our case here, all right, so if you're looking at the formula, so again, you can use the formula to match, or you can look at how many lone pairs the central atom has. So we're looking up here, and so we'll have nitrogen. It's got 3 hydrogens on it and 1 lone pair. So we're looking at this middle one here. See, there's 1, 2, 3 peripheral atoms and 1 lone pair. So it's a trigonal pyramid this time. Okay, so let's draw out the 3-dimensional shape here. Okay. All right, so we're going to put nitrogen in the center like that. Okay, and then I'm just going to, because it's trigonal, it's got the steric number 4, so I'm just going to show the 4 things attached. Okay, so again, one of the things, okay, one of the items attached is the lone pair. The other ones are hydrogen. The 3 other spaces are hydrogen like that. Okay, so we have our lone pair. There it is. Okay. Then we have our peripheral atoms. There they are. So you don't add these circles normally, but I'm just trying to get you comfortable with where you're looking for these items. Okay, and then I'll stop drawing them. So don't draw them as your final product. Okay, so we have our shape here. So we called it a trigonal pyramid. Okay. And then from there, we're going to look at the molecular shape now. Okay, so now we're going to move to drawing the actual three-dimensional shape. Okay, so again, if you're just wondering why are we drawing a shape and then drawing another shape here, so the electronic geometry, we're going to use a steric number to kind of, look at, okay, kind of what kind of shape is it going to take on, right? So we're noticing here, if it's steric number 2, it's a straight line. 3, it'll look like this. 4, it'll look like that, right? And then from there, we're going to get to the point where we can actually label the molecular shape. Okay, so here, so once we get the electronic geometry shapes, the tetrahedral shape here, what we're going to do here is we're going to just draw just the hydrogen, just the peripheral atoms here. Like that. Okay, so we're not going to draw the lone pair. Okay, so what's happening here is that now we have, a hydrogen sticking straight out of the page, a hydrogen sticking behind the page, and then we have a hydrogen in the page. Okay, so we're going to take a look here now at the names. So we're looking at a peripheral atom with 4 things, steric number 4. So we're looking here, which one of these has just the one lone pair? And so we'll look here, and you can see that that's this one here, the trigonal pyramid. Okay, so that's the name of the shape here. So we'll add that down here, trigonal pyramid. Like that, okay? All right, so that's the molecular shape name. And then from there, we'll look at the bond polarities. Okay, and then, you can, just so that you stay, so we'll move on to the bond polarities here. So we'll look specifically at just the nitrogen-hydrogen bond here. We're going to look at the electronegativity values. So look on your periodic table. So nitrogen has electronegativity value of 3, and hydrogen is 2.1, like that. So when you take the difference here, you're going to get 0.9 for your electronegativity, right? So anyway, so the main thing here is I want you to show the partial charges here. So since nitrogen has a higher electronegativity value, it's going to be able to pull those bonding electrons closer to it. So you're going to get a slightly negative end here and a slightly positive end here, like that. Okay, so knowing that, what you're going to do here is, okay, so we know that it's a polar covalent bond. Okay, so don't forget to analyze just the bond within the molecules. Okay, so if there's multiple different bonds, then yes, analyze all of them, okay? All right, so we're seeing the partial charges. So now we can go back to the previous diagram here, and we can add these partial charges on. So the nitrogen is going to be the negative end of each of the negative nitrogen-hydrogen bonds here, okay? So we'll do that, and then here, if we look at nitrogen, hydrogen through the middle here, nitrogen is going to be negative, hydrogen would be slightly positive, and then nitrogen is slightly negative and slightly positive hydrogen here. Okay, so once we kind of add these to the diagram, we can see that there is a negative end, and then there's a positive end, right? So there's a negative end where the nitrogen is, and then all these hydrogens, remember, are bending away because of that lone pair, right, from the electronic geometry. That lone pair bends them away, so it's almost kind of like a triangle, like a pyramid, right? That's why it's called a trigonal pyramid. So they're bending away, so you have a negative end and a positive end. Because the overall molecule has a negative and a positive end to it, that's what we can conclude here with the last the column here. So for the molecular polarity, is this going to be a polar or non-polar molecule? And you will say yes, it is a polar molecule because we have the slightly positive and slightly negative parts of the molecule. Try another example here. So again, we're looking here. We got carbon, we got hydrogen, and oxygen here. So let's again start building our Lewis diagram. So carbon has bonding capacity of 4. We got a couple hydrogens, like that, and then we have an oxygen. Okay, so we need to draw our Lewis diagram. Okay, so we're gonna Okay, get the electrons to share together. So hydrogen will come in here, bond right there. The other hydrogen will bond right here. Okay. All right. Now the oxygen, it needs a couple spots here. So carbon happens to have 2 left over. So there and there. Okay. So now we need to draw our Lewis diagram here. So this is an interesting one, right? So we have carbon. It's going to be double bonded to, here, I'm going to do it. Here. Yeah, it's going to be double bonded to oxygen here. And then we have our hydrogen. And we have our hydrogen like that. Okay. All right. So from there, that's our two-dimensional structure. So we are trying to figure out the geometry of this molecule, okay? So we're going to use our ax notation here. So again, carbon is the central atom. So here, we'll just go like this. Carbon's the central atom. All right, the peripherals, okay? We have a couple different peripherals, but in the end, there are, so peripheral atom. So just look at it as, yeah, like, just count them all up, okay? So we have X, we have 3 of the peripheral atoms. We have 1 O and then 2 hydrogens, okay? And then if we're looking at the lone pairs, how many lone pairs are on the central atom? Remember, the carbon is the central atom, so there's none. All of the electrons have been used up. Okay, so remember how above I was like, if there's 1, you can drop it, right? We know there's still 1, but if there's 0, you make sure you write the 0 on. Okay, so this is our ax notation this time. So it's AX3, E0. Okay, all right, so go to our steric number. This is going to help work towards figuring out our shape. So 3 plus 0 is 3. So let's look at our electronic geometry table. Here it is. Okay. So yeah, in the end, I ended up adding the names. Like when we're looking at the electronic geometry, okay, we're looking at tetrahedral because it was steric number 4. In our case here, we have a steric number 3 this time. So we're looking at our electronic geometry table. We have our trigonal pyramid, trigonal planar. Okay. All right, so let's add that. Okay, so trigonal planar. So this is the electronic geometry. Okay, but in the end, this is just to help us get to the molecular shape. This is the molecular shape, and the name of the molecular shape is the more important part here. Okay, all right. So our trigonal planar is showing us that. So now we'll look here. So we have one of these scenarios here, okay? All right, anyway, so we'll just draw this out first. Okay, so trigonal planar, you have the 1, 2, 3, kind of like they're all in the paper, and they're not sticking out forward or backwards, okay? So let's draw this out. So we have carbon, we have the oxygen, and then we have the hydrogen like that, okay? So it's just straight across like that with the hydrogen, and you're going on like an angle here, okay? So all 3 of them around. All right, so we know it's a trigonal planar shape. So now we're getting to the actual 3D molecule and the actual name. So we know it's a steric number 3 this time, right? So we're looking at these, and what do we have in our scenario? We do have 3 different atoms attached, okay? So we're not going to be like the second example here where it's got a lone pair and then 2 peripheral atoms attached. So in our case here, we would call this trigonal planar, okay? That's a trigonal planar molecular shape as well, okay? So trigonal, I'm just going to write the name first, planar, like that. Okay, so our electronic geometry shape and our molecular shape are the same names. Okay, so I'm just going to draw them out here. Okay, so all of these, see how the lines are all just straight lines? That's why these are all in the paper, okay? They're not sticking forward, they're not sticking behind, and so forth. All right, so now that we have our shape here, okay, now we're going to look at analyzing the individual bonds within the shape here, okay, this molecule. So, so we'll start with the carbon to oxygen bond, and then we'll analyze the carbon to hydrogen just to see what's happening here within those bonds, okay? And then we're going to label, what kind of bond those are, and then from there we'll step out and look at the actual molecular polarity, okay? So we'll just look at carbon to oxygen. I know it's a double bond, but just look at carbon to oxygen. So again, look on your periodic table, and you're finding that you have 2.5, so you have 2. So here I'll just do it about 2.5 for the carbon and 3.5 for oxygen. Okay, so we don't need to take the difference today, or if actually no, you do need to take the difference. So from there, if you need to calculate it out, I'll get a value of 1, and so that will mean that it's a polar covalent bond. Oops, I'll do it in red just like above. Okay, polar covalent bond. Okay, so just looking at the carbon to oxygen bond here, we do have a polar covalent bond. Okay, so there's not going to be a balance of the tugging on the electrons. Oxygen has a higher electronegativity value, so it's going to be able to pull the electrons towards it. Okay, so it's going to create a slightly negative end to that bond. All right, the other bond that we have to analyze is the carbon-hydrogen bond. Okay, so if we're looking at that, carbon is 2.5 again, and hydrogen is 2.1. Okay, so if we take the difference there, we get a 0.4, so that makes it a slightly polar covalent bond. Okay. All right, so now that we looked at the bond polarities, so just what's happening with the bonds, the different bonds within the molecule, what we're going to do is step out now, and we're going to add the partial charges to the diagram before, and then we're going to determine if it's got a positive pole and a negative pole. Okay, all right, so let's go back to reading here. All right, so here, carbon to hydrogen, what did we notice? So, carbon to oxygen, we noticed that oxygen had the higher electronegativity value. So you're going to have a partial end here and a positive end here, like that. Okay. All right, and then so anyway, here, why don't we add those? Why don't we add those to the diagram here as well? Okay, so positive and negative and positive. Then here, this is the positive and that's the negative. Okay. All right, so that's with the carbon to oxygen. So now if we're looking carbon to hydrogen, what are we noticing here? Well, this tug of war with the electrons, carbon's going to win this time. Okay, carbon lost against oxygen, but carbon's going to win with hydrogen. So hydrogen's going to get that slightly positive end. Carbon will get the slightly negative end. Okay, all right, and then same thing going this way as well. Okay. So now what I want you to do, I know it's getting a little messy here, but I want you to look on the very outside of the shape. So back here when we looked at ammonia, whoops, we have ammonia here, we found that there was a negative end here and a positive end down here. So we had a negative pole and a positive pole. So with our new shape here, we're seeing a lot of stuff happening with the carbon, right? Sometimes it's negative, sometimes it's positive, depending on the bond. But again, if we're looking on the very outside here, we're noticing that this end is negative and this end of the molecule is positive. See? And again, we're just looking at the outside. We're not looking at the stuff inside here. So positive ends here, negative ends there. We do have a positive negative pole. Okay, so if we have poles like that, then we can say our molecule is a polar molecule. So we have polar and non-polar end. Okay, let's do one more example, and hopefully after that you'll feel confident with what you need to do. Okay, so again, a lot of steps here, involved in drawing the shape, but then some of the stuff at the end, it's kind of stuff you've already done, so we're just kind of applying that information now in order to determine overall polarity, okay? All right, so here is another one here, carbon, again, 4 bonding sites here. Chlorine, we saw that, it has 7 electrons, but 3 pairs there, 6 of them are paired up, and that leaves the 1 bonding site like that, okay? All right, so I have 4 of these chlorines to draw. So I'm sorry, I don't think I have enough space. So what I'm going to show you here is the one chlorine comes in and attaches like that. Okay, so the other chlorines will stick on to the other sites of carbon, and then you end up getting this shape here. Okay, so again, this is the Lewis structure. It's just a two-dimensional structure. Yeah, so we want to move and see what it looks like three-dimensionally. Okay, all right, so let's find the X. X is the carbon, that's the central atom. Okay, X are the peripheral atoms, the ones that attach to the central atom, chlorine in this case. How many are there? 1, 2, 3, 4. Okay, and then we're going to look at going back to the central atom, carbon. Are there any lone pairs? Are there any non-bonding electrons attached? No, so 0. Okay. All right, so now steric number, add those numbers, those subscripts up, you get 4. So it's a tetrahedral shape again. Okay, so we'll look at that. So this is a tetrahedral electronic geometry shape. Okay, there. Okay, so we can make a quick, so diagram here. So we've learned now, chemists will draw 2 in the page, and they will draw 1 coming out of the page and 1 going behind the page like that. Okay, so yeah, so our ax notation steric number have brought us to here, to this shape here. Okay, so so what we've always done from electronic geometry shape to molecular shape is we kind of, we don't draw in the lone pair that's sticking out, okay? But in our case here, we don't have a lone pair, so we're just going to keep drawing our shape like this. Okay, put the peripheral atoms on, the chlorines. And then we're going to go and look for the name. Okay, so we'll look up here at the name here. So again, which one? So it's steric number 4. And so we're looking at these ones here. And in this, our example now, we do have 4 peripheral atoms. Okay, so this one is an actual tetrahedral. Okay, I know we've seen that word before already with when we're trying to find the electronic geometry. But again, we want to know the molecular shape name. So in this case here, it is tetrahedral. Okay. Right? We've seen other ones that were tetrahedral for electronic geometry, but then they had a different name, like it was bent or it was a trigonal pyramid and so forth. Or actually, we haven't seen a bent one yet, but okay. All right, so now that we have our molecular shape, now we can kind of analyze, okay, are we going to have a polar or non-polar molecule here? And we're going to determine that by looking at the bond polarities, okay? So let's look at carbon to chlorine. Okay, that's the only type of bond. There's 4 of them, but that's the only type of bond we have here. Okay, the previous one we did had a carbon oxygen, carbon hydrogen, so we had to analyze both. But in our case here, we have a carbon chlorine only to deal with or to analyze. So our carbon is 2.5 for electronegativity, and our chlorine is 3.0. Okay, so in this battle here, we're going to find that the chlorine is going to be the stronger one here to pull the electrons over. So when you do that, you're going to have a slightly negative end here and a slightly positive end here. Okay, so definitely going to have some sort of polar bond here. So if we take the difference, we get a 0.5 difference. So you can call this a polar covalent bond. Okay, so when I'm asking for bond polarities, I'm literally asking you to look at all the little pieces that make up this compound and analyze what's happening within those bonds. Okay. But then you want to step out and look at what's happening to the whole thing now. Okay, so looking at it in 4 different pieces, let's look at it as one big piece. So here we go, carbon is positive, slightly positive. This chlorine will be slightly negative. Now looking this way, slightly positive, slightly negative, slightly positive, slightly negative, slightly positive, slightly negative. Okay, so again, these are both nonmetals. They are not strong enough to pull the electron right off, so they end up sharing, but there's this unequal sharing, right? If you have a higher electronegativity value, you can pull those electrons closer. Okay, so now I want you to analyze the shape. Okay, so we're not looking at the inside of the shape, we're looking on the very outside. So in the past, we've seen, with these other examples, we've seen like a positive and a negative end, like I don't know, like the top is negative and the bottom is positive, right? But in this case here, we have a positive middle, but we're looking always on the outside. Because again, we're going to move into some study where we're studying a molecule comes close to something, and depending on how it is behaving on the outside of the molecule, it's going to interact with other molecules in a certain way, okay? So what you're going to do here is you're looking at the outside. See how it's all negative, 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 right? So the whole outside is negative. So in that case there, because the whole outside is negative, we don't have a positive and a negative pole, so we don't have poles, right? Sure, there's some charges going on here, but we don't actually have opposite poles here. So in this case here, even though the bonds had polarity to them, the overall shape doesn't have a pole, like polarity to it. So you would call this a non-polar molecule. And people will, after a while, looking at these, will, oh yeah, it's pretty symmetric, right? So that's why, yeah, you're not going to have a different slight partial charges here. Okay, so, all right, so there's a bunch of examples there. This is definitely a lesson where you want to keep kind of playing back certain parts and then doing several examples, okay? And then getting comfortable with, naming the things, identifying which one it should be. It depends, again, on those electrons that aren't involved in bonding. They end up distorting, causing the shape to change. And like if you're looking here at the steric number 4, you have all of these have 4 things on the central atom. But depending on what is on the central atom, you're going to get the shape changing to a different shape and going to different angles. Okay, so when you have 4 peripheral atoms, you get a tetrahedral shape. But when you get a 1 lone pair like that and 3 peripheral atoms, you're going to find that that lone pair, it needs space. It needs for the other things to get away. So it'll push these other ones away. So you'll get this kind of pyramid shape with the other atoms. Okay, and then what if you have 2 lone pairs? So 2 lone pairs, you're going to end up with this bent shape. So you're looking at something that would have looked like a straight line normally, but now it's a bent shape because these lone pairs are really kind of bending those other things away from it, so it can have its, so that repulsion is lower. Okay, all right, so yeah, practice lots, and then when you're ready, try the checkpoint.